In this video, we want to use the method of partial fraction expansion to take this single term here and expand it into the sum of three terms shown here. We're doing that just because it's helping to solve a circuit analysis problem that I show a link to below if you're interested in checking that out. For the purposes of this video, we're just going to show the partial fraction expansion. Okay, so what is partial fraction expansion? Well, let's look at it kind of in reverse. Let's say we started out with an expression that looked like this, and I asked you to combine those three terms into a single term. Well, what would you do? Well, you'd write a common denominator. You'd take this term, and this term. You'd make a denominator like that. Then you would manipulate these numerators and combine like terms, and you would end up with something in the numerator. Now, if you take the denominator here, it turns out if you combine all that together, you will end up with s cubed plus 6s squared plus 10s in this case. Okay, so now let's take it and do it in the other direction, right? Let's say we start with this and we want to go towards this, okay? Well, we can do that as long as the order of the polynomial in the denominator, in this case s cubed, so our order is 3, as long as that is greater than the order of the polynomial in the numerator, okay, which is s to the 0, so 0th order in this case. V is a constant in this problem. It actually stands for voltage in the problem that we're solving. Okay. What we need to do is then just take and factor this cubic into its three component parts. The first part is easy, right? There's an s in each of these. We can just pull out s there. What we're left with is a quadratic here. And if we throw that quadratic into the quadratic equation, it turns out we get two complex roots, right? Because you can see here under the radical 36 minus 40, right? The square root of minus 4, well, that's minus 2i. Divide everything by 2, and you get two complex conjugate roots, minus 3 plus and minus I. So if we take our variable s and we subtract our roots, we end up with factors that look like this in the denominator. Okay, so we take our original equation, we factor it out in the denominator here, and we write it as the sum of these three terms where we are trying now to solve for a, b, and c. Okay, over here our denominators are first order, and which means that our numerators can only be 0th order, right? They can only be constants in this case. So in partial fractions, if I had, say, a second order here, that polynomial in the denominator, I could have a first order solution up here in the numerator. Okay. Okay, so all we need to do then is manipulate this equation to find a, b, and c. How do we do that? Well, let's find a. Okay. The strategy here is going to be to eliminate b and c and just isolate a, and then plug in some values over here on the left side and find out just what a equals. Okay. So to get a alone, let's multiply everything through here. We're going to multiply by s. And then we're going to take s and we're going to set it equal to 0 after we've multiplied it through. So when we multiply through by s, we're going to end up canceling the s's here on a, and we're going to have an s over here and an s over here, right? But that s is going to be set equal to 0. So b and c are going to drop out of this equation, and the only thing we're going to have left on the right-hand side is just a. Let's see what happens on the left-hand side. In this case, let's bring the left-hand side down in this form, okay? So here it is down here in this form. And let's multiply by s, right? Cancel the s on the numerator, cancel the s in the denominator, and set the remaining s is equal to 0. S squared is 0, and 6s is 0. So that leaves 2v divided by 10, which is just v over 5, and of course that equals a. Okay, let's find b. We're going to do the same kind of a strategy. We're going to take and multiply this whole equation through by the denominator of b. Right, we're going to multiply through by the denominator b, s plus 3 minus I. S plus 3 minus I. That's going to cancel here and leave just b here. We're going to end up with that term here in the numerators for a and c. Okay, well, how does that help? Well, if we take and we set s then to minus 3 plus I, plug that minus 3 plus I in for s. So plus 3 minus 3 is 0. Minus I plus I is 0. Right? So when we set s equal to minus 3 plus I, this term becomes 0. Multiply everything through by that term, cancels here. The term shows up here, the term shows up here. We're going to set that term equal to 0, so this term disappears and this term disappears, and we're just left with b on the right-hand side. Okay, let's do the left-hand side. So let's bring down, we're going to essentially bring down this equation down here. Okay, so the 2v comes down. We're going to multiply through by s plus 3 minus I. And then we're going to set s equal to minus 3 plus I. So this s is set equal to minus 3 plus I. Bring this term down. Take this s, set it equal to minus 3 plus I. Bring the 3 plus I down here. Okay. This term and this term cancel. And we are just left with something here we need to simplify, right? And when we simplify that, we get v over minus 1 minus 3i. Because we don't want to leave the complex number down here in the denominator, we'll just take and multiply the top and bottom here by the complex conjugate of this. So we'll multiply by minus 1 plus 3i over minus 1 plus 3i. When we do that, we get v and minus 1 plus 3i in the numerator. And then in the denominator, the imaginary parts cancel, and we just get this 1 squared plus 3 squared is 10. So here's our left-hand side, and it equals b. Okay, for finding c, this is the answer. The way you get there is going to do the same thing. You're going to multiply everything through by this denominator. You're going to set this term equal to 0 so that this and this term drop out, right? So how do we do that? S is going to be set to minus 3 minus I. These terms will drop out, and some things will cancel here. We'll do some algebra, and you will end up with this term. So I'm kind of leaving that as an exercise for you to do if you so choose. Okay, putting it all together, we have a equal to v over 5. B is this, c is this. Just plug that in here, here, and here, and write it down here. There's our nice ugly expression. It kind of seems ugly, right? Bring down our original here to just say that this single term now is equal to the sum of these three terms. And believe it or not, even though this looks a little ugly, it's going to help me solve that circuit analysis problem. This one would be a little tough to solve that circuit analysis problem in that form. Okay, that's partial fractions.